we know when we look at exponents, and there's a product of exponents, we can change those around a little bit. And this is something that's going to be useful for you if you're a person that's interested in going to higher level math courses. Manipulating exponents to rewrite something that's a little bit more convenient to work with is a good skill to have. So if I look at that right there, okay, I don't like it written as e to the 2x. I like seeing it as e to the x squared. Okay, I know that it's okay to do because when I evaluate e to the x squared, or I simplify it, I have a power to a power, and I just multiply those powers, right? So x times 2 is still 2x, right? Okay. But I like doing that. You're going to see here in a moment why I like doing that. So now it's minus e to the x minus sin 6 is equal to 0. Now the reason I like doing that is because now this thing is in quadratic form. Okay, it's some object squared, some object then the same object to the first power, okay, and then plus or minus your constant. Just like ax squared plus bx plus c equals 0, where a, b, and c are just constants and are coefficients, but the x squared is some object x to the second power, and the x to the first is some object the same x, but now raised to the first power. Okay, so anything that is some object squared plus or minus some object to the first plus or minus some constant, that is quadratic in form, right? And that's what we've got. Just the objects are e to the x in this case. So what I like to do to solve these, I think the best thing for you to do is let u equal e to the x. We've done that before, right? Remember u substitution?
Yes.
Okay, so if we let u equal e to the x, we can then rewrite this thing as u squared. Now u is my object, minus then u to the first, minus then 6 equals 0. Does that factor, is that a little bit more obvious of how to factor than what e to 2x minus e to the x minus 6 was? Yeah, okay. Now if you've got the capacity in your mind that when you see this, you also see that at the same time, and you don't want to have to write that stuff in the middle, you can. I mean, you can factor that initial one perfectly fine. But I think these techniques of simplifying the way it looks might be a lot easier for some of us. Okay? How does u squared minus u minus 6 factor? U minus 3, u plus 2. So then u is equal to what? 3 and negative 2. Okay. Now, that's not my answer, right? Because what was the question in regards to what variable? X. And we just solved for u. Okay? So if u is 3, and I back substitute, okay, so u equals 3, but u was e to the x, right? So now we have e to the x equals 3. It's an exponential equation now, right? It's a lot simpler of an exponential equation than what we started with, but it's still an exponential equation. The reason we like that one a little bit better is because there's only one exponential component on the left-hand side, right? And I can now, to get those exponents, okay, that are variable, to get that variable exponent out of the exponent location, what do I need to use? I use a logarithm. Now, which one would be the most appropriate since e is the base of my exponential? Natural. So I'll use natural. I'll take natural on both sides. Okay. And if we remember from Friday or Thursday, ln of e to the x is just what? Just x. Okay. If you guys remember log base e, that's ln. Okay. Of e to the x is equal to what? Well, e raised to x is going to come back and give me e to the x. So that's how that substitutes ln of e to the x is just x. And then obviously the right hand side was ln of 3. Alright, so that number is fine. ln of 3 is perfectly fine. We'll talk about how I know that's perfectly fine here in a moment. But that was only one value for u, right? U was 3, but what do we also find u to be? -2. So I'm going to go through the same process. U equals -2. Okay? That means then e to the x is equal to -2. That means when I ln both sides, I get ln of e to the x equals ln of -2. And that just gives me x equals the natural log of -2, right? That is not okay. Because of what reason? Good. Okay? You cannot take the logarithm of a negative number because the logarithm, remember, the logarithm is the inverse of an exponential, right? So if I have an exponential, let's say e to some x value that looks like that, okay, then the logarithm is going to look something like that. Well, does that logarithm ever get to the left of that line right there? No, that line is x equals 0, right? So it never gets to the left of there where x would be -1, or in this case -2, or anything that's negative, okay? And it can't even be 0, okay? So you cannot take the natural log of a negative number, so that's kind of an extraneous solution that just develops because of the algebra. Does that make sense? Okay? You always, when dealing with logarithms, it's just like square roots. When you have a square root equation, you get solutions. Don't you always have to plug those back in and make sure that they work? Okay? Same idea here. Okay? We always need to check our answers, see if they make sense to us. In this case, we want to make sure that when a logarithm shows up in an answer, that we're taking the logarithm of a positive number. All right, so how do I check myself calculator-wise? Let's go open our calculator up, and we will use, I'm not sure if I showed this technique to you guys yesterday. I think I've used it before. That was weird. Okay. So we just found out that our answer was ln of 3, right? We'll type ln of 3. Then I want to hit the STO button, which means store. And we're going to store it as x. And you store it as any variable you want to. If you hit alpha and then whatever letter, you can store it as A, B, C, whatever. And then we're going to hit enter. And it just shows me then what ln of 3 is. Okay? And now what it means is that every time the calculator sees x, it's not going to use x anymore. It's going to use 1.09. Does that make sense? Okay? So my equation that we started with was e to the 2x. So I'm going to type that in. And then it was minus e to the x. And then it was minus 6. And when I hit enter, if ln of 3 is my answer, what should I get? I should get 0. Okay? So that's, one way of using your technology to check yourself. Obviously, another way would be to graph this thing. Okay, let's see what... See what e to the 2x minus e to the x minus 6 looks like. Come on. Kind of looks like that, right? Okay. We're asking where is it equal to 0? Well, if we go to intersect, I'll just hit zeros, so roots. Gives me that number right there. That number rounded to 10 decimal places is exactly the same thing as that ln of 3, 1.0986. Okay. The only thing there is, obviously using GeoGebra, if you use Desmos or whatever, it doesn't put it back into like the exact form. It doesn't put it as ln of 3. It puts it as its approximated decimal. But it is an option. Maybe I'm on a you know, think about ACT stuff. ACT stuff, maybe you don't remember how to do the particular problem, but you know that you can use your calculator. But all your answers on the ACT, A, B, C, D, are in exact formats, right? So using like ln of 3 and ln of 2 and stuff like that. Could I go through with my calculator and find the answer of 1.0986 and then take every A, B, C, D of the ACT question and change those into decimals and then match up the decimals, okay? There's a lot of stuff to do there, but it might eventually be a little bit quicker than going through, you know, the U substitution process here and all that kind of stuff. Let's see some logarithmic equations. You're going to see, you know, one or two of these in your homework, but they're all the same. Okay, you know, see this one here. Just in this one, what you would probably want to do, and I'll just start you off for this one. But if I rewrite this as e to 2x squared plus 4 e to the 2x minus 21 equals 0. I always try to put in my parentheses the object that is showing the quadratic format, right? Does that kind of make sense? What would I let u be in this case then? Yeah, e to the 2x. So I would go through substitute, so I get what, u squared plus 4u minus 21. That's going to factor to u minus 3u plus 7. So then I get u to be 3 and u to be negative 7, and then I put the e to 2x back in. I just go back through logarithms and solve. Does that make sense? Okay. They're all very similar, regardless. And you know, last one we just had u was e to the x. Okay. And when we apply the logarithm property, we took the natural log of both sides. We got just x left over, right? If I take the natural log of e to 2x, all I'm left over with then is 2x. Does that make sense? And then you would divide both sides by 2 to get just 1x. So that is kind of how you would start that problem. I think that usually ends up being the biggest issue people have is not necessarily going through the process. It's making the distinction of what we should let u be. Okay? And we always want to let it be something that when we can square it, okay, and still get back to that first term. Okay? We also want it to be something at the same time to where you know, it's some object where this is to the first power and this is to, you know, twice that power. Okay, there's always got to be a 1 to 2 relationship there with those things to be quadratic in nature. So you might see a few of those in section 4.4 and 4.5. And obviously, if you need to, we can come back and talk about those again after break. But these are logarithmic equations. And logarithmic equations, we're going to use similar techniques as what we dealt with in regards to exponentials. Whenever you solve equations, go back to, you know, algebra 1. If I have 2x equals 10, what are you going to do to both sides? Divide by 2. Because what you're seeing is a product of 2 and x, right? So you use the inverse operation of division, correct? Okay. If I have x plus 5 equals 12, what are you going to do to both sides? Subtract 5, because you see addition on the left-hand side, and addition's inverse is subtraction, right? So you're using inverse operations to undo something. Well, if I have a exponential, like the equations that we were doing previously, yesterday and just now, those were exponentials, and which technique or which inverse did we use to undo them? Logarithms. So now if I start with a logarithmic equation, how am I going to undo logarithms? Exponentials. Okay, I use the inverses. Okay, so one of the kind of easiest type is recognizing again really a one-to-one relationship that basically says if I have, let's do one that's really easy. Let's just say I have log base 10 of x equals log base 10 of 3. Because everything is identical in regards to the log portions, can I just say, in order for the left-hand side to end up being exactly the same as the right-hand side, that x could be 3? That makes sense? We talked about that yesterday with the exponentials.
And I made a comparison, I think, in this class to, if I had 2/3 equals x over 3, there's a 1-to-1 relationship here that says 2 has to be the same thing as x, doesn't it? Okay, so it's the same concept here. Okay, how do I get the left-hand side to match visually the right-hand side? And the x and the 3 have to be the same. So when you see questions like this, when you have log, and this, the only way you can apply this and use this, if on the left-hand side you only see the log word one time, and on the right-hand side you only see the word log one time. Okay? If you were to have multiple logs over here on the right-hand side or on the left-hand side, you'd have to condense those using your laws first before you could apply those. But since that is identical to that, okay, what can I say about 4x and x squared? 3. Okay, so 4x equals x squared. Now, is that something I can solve? Something like that, don't we? Okay. Whenever I see x squared, I want to instantly think factor. So that thing factors is a GCF of x. So I get x to either be 0 or I get x to be 4. Okay. Now, if x is 0, plug 0 in there, I get log base 2 of 0. Well, is there anything I can take 2 to raise it to and get 0? No. Okay. 0, when you look at your logarithm function on a graph, x can never be 0. X is a vertical asymptote. X equals 0 is a vertical asymptote. Sorry. So even though that solution shows up, it is a non-real solution. Okay, so we're going to cancel that guy out. Okay, x cannot be 0 in this case. But can x be 4? Yeah, if I plug 4 in, and this is the law, just how you would maybe check yourself. Plug 4 in here, I get log base 2 of 16. Does that equal log base 2 of 16? Yeah. Okay. Now, the logic is I could do the exact same thing with 0. If I plug 0 and I get log base 2 of 0 equals log base 2 of 0. But the concept is, the logic is that you can't do that. Okay? You are not able to take the logarithm of 0. Okay? So that's, you can't necessarily always be just all about just being able to replicate steps. You have to have some fault behind it. Okay? And that reminds me that there are domain issues with logarithms. Is that something we can do? Is that a pretty easy type of question? Okay. Now there may be other ways that we could approach that question, but that's, I think, the simplest. If we look at some guidelines for solving for logarithmic equations. Now these are just guidelines, just like when we dealt with exponentials, we just had guidelines. So guidelines are not kind of set in stone, they're just, things that may help you. Okay? It says isolate the logarithmic term on one side, okay, if it's possible. Okay? But the first thing you might have to do is combine logarithmic terms. So you might have logarithm written 2, 3, 4 times on the left-hand side. And you have to condense that using our laws down to one logarithmic term. Okay? Step 2 and 3 are then basically showing you use the inverse operations. If you have a logarithm and it's one logarithm on the left-hand side, you can use your definition of a logarithm then to change it to an exponential, and you can solve it. Okay? And that will kind of open your eyes to what x is. And essentially, once you do that, once you use the exponential, you develop either a linear equation, a quadratic equation, a cubic equation. You develop something that's algebra 1 or algebra 2 type math. Okay, but those are guidelines. Those are what we're trying to follow. But again, every once in a while there might be kind of special situations, special scenarios that those guidelines maybe can be altered a little bit. All right, so just do a really easy one. ln of x equals 8. We're trying to figure out what does x have to be. So when I take the natural log of it, I get 8 back. Okay? And here is the situation where, if you guys remember back to last week, I said every time I see ln in an equation, I always change it to log base e. Okay? Because it's going to allow me to visualize the correct algebra here. So I'm going to rewrite this as log base e of x equals 8. Okay? And now that I've isolated the logarithmic term over here, that's all by itself, right? Once I do that, I'm going to use the definition. I'm going to use that log base b of x equals y if and only if b to the y equals x. So I'm in this format there. That's what that blue equation kind of models. I want to change it to that. So we take e, which is our base, right? We raise it to the exponent of 8, and that's going to come back and give me what? X. Did we just solve for x? Yep. Okay. So it develops an equation that is, an algebra 1 or algebra 2, algebra 3 equation. That one, it gives you kind of a trivial equation. There's nothing to do after you apply that definition of logarithms. It isolates x right away. But does this make sense? If I look at plugging this answer back in, okay, so I have log base e. Now it said x here, right? Well, plug your answer, e to the 8th. Should that be 8? Yeah. Does e raised to that number come back and give me that number right there? All right. You can also do it this way. You can take your calculator. You can say, hopefully we don't have to do this way, but it's an option. I can type in e to the 8th, store that as x. Okay, it's that number there. So if I take the natural log of that number then, so natural log of x should give me back 8. Okay. So that's kind of, I think it's interesting if I take, e raised to the 8th power, so come back and give me that number right there. Is that doable? Okay. Now, that's kind of an elementary, kind of basic logarithmic equation. Not a lot of work there. Okay. Let's come down to this one. There's more stuff involved in this second one, and maybe one of the first things you want to think about is that when you solve this one, there's going to be some information that is important in regards to the type of number x is allowed to be. You can only take logarithms of what types of numbers? Positive, right? And this might kind of parallel to what we've talked about with radical equations. If we do a radical equation, you have two options. You can either look at the equation first and look at all the individual domains and say, okay, I'm looking at all these individual domains, which are going to tell me the values of x is going to be allowed to be when I get an answer, right? Or, probably most of us are probably more comfortable solving the radical equation, getting an answer or multiple answers, and then plugging all those back into the beginning and see if we are allowed to use them. Does that make sense? I think, and we can do the same thing here with logarithms. You can either just kind of blindly answer it, go through the process, get an answer, and see if, do I plug it back in, am I taking a logarithm, ultimately have a positive number, okay? Or, you can say, I know that 25 minus x has to be a positive number. So then when I solve this, I know that x has to be less than 25. So if I go through and I find an answer that's like 36, that tells me that 36 is an extraneous solution. It doesn't really work. Does that make sense? Okay? So it's nice. You can't always do that really easily, but when your argument here is linear, okay, it's or maybe even quadratic, so you might have the ability to see it with a quadratic. It's kind of nice to know what your answer should look like prior to doing the problem. So this one here, it's already, the logarithm is already isolated. There's only one of them, so those steps are already done for you. So now you're just going to apply the definition of a logarithm. So you're going to take that 2, and you're going to raise it to that 3. And that's going to come back and give you what? 25 minus x. Okay? So what's 2 cubed? 8. So we get 8 equals 25 minus x.
So I get negative 17 equals negative x, so x is what? 17. Is that answer less than 25? Yes. So I know because it's less than 25, when I plug it in, it's going to give me a positive number in the argument. What's 25 minus 17, or 25 minus 17? 8. Can you take the logarithm of 8? Yeah. And does it make sense? Does log base 2 of 8, does that equal 3? Yeah. 2 to the third comes back and gives me 8. Okay? So that's kind of how you would address those types of problems. Does that make sense? All right. Now they obviously get a little bit more complicated, so the next one will add one step. Okay? When we look at something, I guess we won't add a step here. We'll do another example. But this one is, if I were to look at this one and try to think about the domain right away and what my answer should look like right away, you're going to have to say x squared minus x minus 2 is going to be greater than 0, right? X squared minus x minus 2 is greater than 0. You guys remember how to deal with quadratic inequalities? Well, we factor it, set up a sign chart, and all that garbage, right? It's a lot of work to just see what kind of numbers I'm going to have for solution, I should have for solution. So my suggestion, when the argument gets a little bit more complicated than usually when it's not linear, just solve it. Solve the logarithm, and then at the end, just go back and substitute. You're going to save yourself a little bit of work by substituting, okay, instead of trying to do the sign chart and all that kind of stuff. But that is one of the purposes of why we learn sign charts and learn polynomial inequalities, so that we can recognize the domain of a logarithm and recognize the types of solutions we should get before we go through the work of logarithms. Does that make sense? Okay. But I think it's, at least in this situation, more work than what's necessary. All right. So you've already got the logarithm isolated. So it's just like the last one. You're going to take this 2, raise it to that thing there, and that's going to come back and give you what? So now can I factor that? That's 4, right? I'll move that to the other side. So I get 0 is equal to x squared minus x minus 6. Okay, and that quadratic we've actually already factored once today. Is that x minus 3x plus 2? So it gives me x to be 3 and x to be negative 2, right? Now here's where you just got to be careful. You have to check your answers. You have to make sure that when I use 3, that it doesn't provide me a negative number inside this argument. Okay? When I try negative 2, I have to make sure it doesn't provide me a negative number in that argument as well. So plugging 3 in, you get 9. Minus 3 is 6. Minus 2 is 4, right? Is 4 an okay number? Yeah. And if you think about it, does it make sense? As log base 2 of 4, is that equal to 2? Yeah. Okay. And now try negative 2 as well. Negative 2 squared is 4 minus a negative 2, so that's plus 2, so it becomes 6. And I get 6 minus 2 again, right? And it gives me 4. So negative 2 works as well. Okay? And the reason for that, and the reason I know those two were okay initially maybe, is if I think about doing maybe a sign chart for this thing, the zeros are at what? Negative 2 and positive 1? Negative 2, positive 1. Would you guys agree that those x values are above and those x values are below? So would you agree that to the left of negative 2, we're okay? Okay. And to the right of 1, we're okay as well? Does that make sense, everyone? Okay. That's what we're looking at there. So that's not, I think, much different than the last example. Just the algebra that you get when you use that definition of a logarithm, that algebra that's developed. Maybe linear, maybe quadratic, maybe cubic, whatever. If it's cubic or quartic, you might have to, in order to factor, you might have to use the rational root theorem. Okay? So all the kind of fundamental
prerequisite algebra that we've developed, that we've established, is fair game when we set these things up. Okay. This one's just one extra step before we can turn it into an example like the last one. If I look at log base 9 of x minus 5 plus log base 9 of x plus 3 equals 1, the one thing you want to pay attention to is make sure that the bases are the same, and just kind of ease your mind. If they're different, we really can't do anything. Okay? We could basically it's outside the scope of this course. So you're going to pretty much see every single time the bases being the same. Okay? So they won't say log base 9 of x minus 5 plus log base 4 of x plus 3. They're going to be 9 and 9. Okay? So when we do this, if we go back to our guidelines, it says you may have to combine logarithmic terms on one side. And it might have to happen on both sides. But in this case, it's only on one side. And I see that plus sign right there. If we go back to Friday's logarithm rules or laws, what does a plus sign turn into? Multiplication. So we can rewrite this as log base 9 of, I'll write it this way first. Right? Okay? So when I do that multiplication, you have binomial times a binomial, we probably should expand that, and this is the reason why, and we'll talk about this in a moment. But let's go ahead and just use our definition of a logarithm now. Can I take 9 raised to that power? Come back and give me that. Okay, now it's all your choice when you want to expand that, but you have to expand that. And the reason you have to expand that is because I currently have that as equal to 9, right? And the only way that you can factor something is if you have it equal to what? 0. So I know that there's a negative 15 that's residing inside this product that's going to combine with that 9. Okay, so I need to expand it. You might think, well, it's kind of redundant to expand it and then factor, but we're expanding, grouping like terms, okay, simplifying, and then factoring something that's new. So I get x squared minus, what, 2x minus 15 is equal to 9. Add 9 to both sides. Sorry, subtract 9 to both sides. Get x squared minus 2x minus 24. So what's x going to be? What does that factor to, I guess, first? X minus 6, x plus 4. So x then is 6 and negative 4. Now just here's where you want to think about your domains. Okay? When I look at this, x minus 5, that tells me that x had to be bigger than 5, doesn't it? Okay? X has to be bigger than 5, and this says x has to be bigger than negative 3. So x values have to be bigger than 5 and bigger than negative 3 at the exact same time. Well, that means they got to be bigger than 5. Can that one work? No. Okay? And like I said, I like to look at the domains of the what's in the argument. I don't know, that's just the way I was taught, but I know some people don't like doing that. So an option for you is to take your two answers. Take 6, plug it in here, and get log base 9 of 1. Can you take logarithm of 1? Yeah. If I plug 6 in here, I get log base 9 of 9. Can I take the logarithm of 9? Yeah. Okay. So that tells me why 6 works. But if I plug in negative 4, I get negative 4 minus 5, which is negative 9, right? Can I take the log of negative 9? No. So the x value that provided that logarithm can't work. Okay. Kind of think about why this works. Think about, we substituted here. I get log base 9 of 1 plus log base 9 of 9 is equal to 1. Okay? What do I have to raise this thing to? What do I have to raise that 9 to get back to that 1? 0. Okay? So log base 9 of 1 is just saying 0, right? What do I have to raise 9 to, that base of 9, to get back to that 9? 1. Does 0 plus 1 equal 1? Yes. Okay. And that might be a reason why we had those properties earlier in the week where we said log base A of 1 is always 0, because that's what that is saying right there. We had the one that said log base A of A is equal to 1, because that's what that one there is saying. Does that make sense, everyone? And it's just a way to then help yourself check your answers to make sure that makes sense. Again, you could also take, -6 and positive, well, I guess, was it positive 4? Is that the answer, or positive 6? Positive 6. You take 6, store that as X on your calculator, and you could type this thing in. Okay? Now, you can only type it in if you have the ability to change the bases, right? Okay? I think maybe we're running out of time now, but maybe later, maybe tomorrow, I don't know. We'll talk about how maybe you could use your calculator if your calculator doesn't allow you to change the base. It's a little bit more complex, but it still works. All right, so this one is kind of a pain in the butt. All right, because of what develops. And I want to make sure we do this because you're going to see one in your homework. Whenever I see ln, because I know I'm going to have to use, inside these equations, I'm going to have to use the definition of logarithm. So whenever I see ln, I rewrite it as what? Log base e. So I go log base e of x minus 1 plus log base e of x plus 2. And that's equal to 1, right? Okay. Now there's addition on the left-hand side, so addition turns into what? Multiplication. So we get log base e. Now I'm just going to multiply it out. So x times x gives me x squared, right? Negative x and positive 2x just gives me positive x. And then minus 2, right? That is equal to 1. Okay? That's doable, right? Okay, just exactly the same thing as what we did in the last one. What you need to realize is that when this happens, all right, you get this argument. This argument might lead to something like e raised to that comes back and gives me x squared plus x minus 2. It provides me a factoring situation, right? Okay. Whatever that algebra means, if this was a minus sign, all this stuff, there would be x minus 1 over x plus 2, right? And then that result ends up to provide me algebra that's a rational equation. Whatever the algebra that you end up with, you have the ability to solve it. It's either algebra 1 or algebra 2 concepts that you develop. But now here, this one's kind of ugly. Because what do I have to get this thing equal to do to the factor? 0. So I write it that way. Because e is a constant, right? It's an irrational constant, but it's always the same number. It never changes. Okay? So I know that negative 2 is also a constant. So those two things are like terms, aren't they? Okay? Now, I'm going to do this. I'm going to go 0 is equal to x squared plus x plus negative 2 minus e. That still says the exact same thing, but now I like to write it that way because now I can see what my a term is, what my b term is, and what my c term is for a quadratic equation. Does that make sense? Okay. When you get a c term that is irrational, okay, negative 2 minus e, that's an irrational number. Do you know two rational numbers that will multiply together to give you an irrational number? No, right? Take any rational, any fraction, any whole number multiplied together by any other fraction in a whole number, you're not going to get an irrational number. Okay? So what happens here is that thing is really hard to think about two things that multiply together to give me that and have to give me 1, right? So factoring there kind of stinks. But what is the one process that will always work for factoring? Quadratic formula. Okay? So we've got x is equal to the opposite of b plus or minus b squared minus 4ac all over 2a. We're going to plug in our information. This is obviously a, that's b, and that thing right there is your c. All right, so just direct substitution. We get negative 1 plus or minus 1 minus 4, a is 1, c is negative 2 minus e, all over 2 times a. Once we have that, we can do a little bit of simplifying. We've got -1 plus or minus. This becomes 1 minus, okay, now that 1 really, it's a product, so that 1 really doesn't do anything, right? So I really have -4 distributed into that -2 minus e, right? So what's -4 times -2? 8. And what is -4 times -e? 4e. 2, so now I get -1 plus or minus √9 plus 4e all over 2. Okay? Pretty ugly answer. Now some people are going to say, well, the 9 and the 4, those are perfect squares, let's bring them out. Because they're being added together, because they got e stuck to them, you can't do that. Because that number, e, it's like 2.7, so 2.7 times 4 is like 11 something maybe, or 10 something. 10 plus 9 is like a 19, right? Okay, or 18 or something. So that radicand is not a perfect square, all right? But here's the issue. One of those will work and one of those will not work. Okay, so if we type those in, we'll type in -1 plus √9 plus 4e. Okay, there's my numerator. Divide that thing by 2, and I get 1.7, right? Now that's my x value. If I plug that in, can I take that as my x value? 1.7 minus 1 should work, right? 1.7 plus 2 should work, right? If I do the other one, if I do the -1, I get solutions that are negative. I can't take the logarithm of those negatives. So the only one I want is the positive version of that. See it? All right, so changing this, we can make that a minus. And now we see -2.7. So -2.7 minus this 1 right here, if you plug it in, you'll get -3.7 as your argument. And you cannot take the logarithm of that.
But that doesn't matter.
You can also check this
Right.
by taking that number, storing it as x. Okay, now I'm going to type in this equation, and when I hit or that expression on the left-hand side, hit enter, I should get 1. ln of x minus 1 plus then ln
I tried this in yesterday. I'm sorry.
Okay, thank you.
I wasn't here Friday. Thank you.
x. You were here Friday.
Well, I was here after.
Uh-huh.
Can you open the math unit back up? Work on it in Rocket time.